Hello, and welcome to another exciting lecture in photorealistic and non-photorealistic rendering. I'm your host, as always, Leslie Aston, and today's episode we are going to dive a little bit deeper into some of the different effects that we can achieve with ray tracing, and some of the ones that with the model we have currently presented we can't do. So just a few notes before we get started into the actual content. Please make sure you check Brightspace as Assignment 2 has been posted. And you'll be happy to note that Assignment 2 doesn't actually include any programming. And feel free for Assignment 2, which is a rendering assignment, to use any rendering tool of your choice. So if you want to use Houdini, by all means, please use Houdini. If you prefer to use Maya, use Maya. If you want to use Pavre, use Pavre. If you want to use Blender, whatever you like. The other thing I wanted to mention is to make sure you keep checking into the resource content on Brightspace, as I'm going to be continuing to post guides, nifty little links, assets, and so on there that will be very useful for not just understanding the material, but doing the assignments in the final project, which I will be posting details about probably in 2 weeks or so. All right. So, where did we leave off then last week? We were talking about ray tracing as opposed to ray casting. And that was, now that we've actually figured out what object in the scene we have intersected, now we actually want to figure out what color that object should be. So what we're trying to do is figure out what the contribution of each of the different light sources in the scene would be to producing the color of that surface point on that particular object. And there's a variety of things that are going to play a role here. You're going to have, of course, the color of the object, the type of material of the object. So is it a diffuse material? Is it a shiny material? How shiny is it? You're also going to have the colors of the lights and the intensities of the lights in the room, and you're also going to need to know how far away from the particular light sources we are in order to produce fall-off effects. So there's lots of different things that we can do with that. And if we use all of those tools that we've listed so far, you can get a really decent image. The problem with just the types of shading, of course, that we've already presented is that everything has a tendency to look really plasticky, which I suppose if you were trying to ray trace a bunch of plastic parts, it's perfectly fine. But we actually want to work on creating photorealistic images. So I want to be able to render realistic versions of glasses, cups, and metal objects, and wood objects, and so on and so forth. So we're going to take a closer look at some of the techniques that we're going to need in order to achieve those looks today. Starting with ye old point light. So in the first assignment, and of course in lecture 3, we had a very simplistic model of light known as a point light. It is a fixed point in space that is emitting light equally in all directions. It's literally a point source. It has no volume, it has no area. It's just a point that emits light. Now, these are actually very easy to implement, and they're very easy to use, and they do a pretty good job of creating nicely lit scenes, but they're also highly unrealistic. There's no such thing as a point light. It's not a real thing. If you look at the light, and I know you cannot see the lights that I'm using to light my green screen, but I've got a like a desk lamp that I'm using as a spotlight. I've got a ring light in front of me, and then I've got a bunch of LED panel lights. Each of these lights has either a volume or an area, and light is emitted in particular directions out of that. So my LED panel lights, being that they're, panels, they do not emit light upwards because there's a piece of wood right there. They emit light kind of in the hemisphere like this. Whereas this light that I have over here, my spotlight, is an actual physical light bulb that would be emitting light in all directions from a volume, because the light bulb actually has a physical shape. So point lights are easy to use and they're very easy to implement, but they and they do light the scene, but actually they're not a real object, and they don't light the scene in a necessarily realistic way. The reason we know this is because shadows from a point light source are very hard and crisp. And to show you what I mean, here's our scene. We have a point light source. This, of course, is in Houdini, as pretty much all of my examples are going to be. So for now, we have a point light source, we have a very basic plane, and then on the plane I have a red sphere that is being lit. And we can see that the area underneath and behind this sphere, so right here, should be a shadow. But because this is a point light source, the shadow is actually going to be very harsh, very sharp edged. And when we ray trace it, that's exactly what we get, a very sharp, harsh edge shadow. Now you can see here that my sphere has been rendered with a lot of polygon shapes. It's not a smooth object, and so we can actually see the fact that the shape I've rendered isn't actually a perfect sphere down on the ground, because we can actually see these polygon lines defining the shape. So that's our point light source. And this is kind of possible, but not really in real life. We never have shadows that are so perfect like this. This is a rarity. In reality, our lights actually have a volume or an area, and they emit that light from the entire surface or the entire volume. And that actually is going to have an impact on the appearance of shadows. So, and I've used here an example from like a classroom, things that we haven't seen in like years now. This is, you know, an area light, a very simple example, just the fluorescent panel lighting that you'd see in a class. And this light source is going to emit light from the entire surface in all directions below it. It's not going to emit light upwards because it's contained in a box. So if we wanted to see, how do you actually compute the contributions that lights like this make? What are you going to do? We can create a light like this very easily. We just create a shape and say, hey, you're now emitting light. Congratulations. Very simple to do. But what impact does that have when we're computing that light's contribution on the color of a particular point on the surface of an object? What impact does an area light have on shadow computations? So we're going to have to model things a little bit differently for area and volumetric lighting. And the solution is actually quite simple. So when we had a point light, to determine if the surface point was in a shadow, we sent, or to determine the light's contribution, we send a ray from the point on the surface of the object towards the light, which is a point, so we can draw a ray directly from those 2 points. And then if we intersected anything on the way, then it was in a shadow, otherwise the light contributed to the color. Okay. It's a little bit more complicated, but it's not that bad. The trick is now, because the light actually has a shape, we're going to need to send more than one secondary ray, because the light may only be partially visible. So for example, if this little box is my light, my hand is here, and there might be some objects underneath my hand that are being partially occluded by my hand because they are blocking part of the light. So we need to be able to account for the fact that the light may not be completely occluded, but just partially occluded. And what we do is we choose a bunch of random points on the surface of the light. So if it's a rectangle, we have the definition of that rectangle. We know where it is in the world space, its coordinates. So we'll find a bunch of random points. And then we are going to send a secondary ray from the surface intersection point to each of those points that we randomly selected from the area light. We will compute the contributions for each of those rays as if they were point sources, and then we average them together. And the advantage of doing this is if the light source is partially occluded from that particular point, you are getting only some of the light. You won't be getting all of the light rays contributing. Fairly simple. And the result is very nice. So here's a lovely diagram. So this is our object, and you can see here we are sending 4 random rays. You want to send more than 4, but just for the sake of the diagram. We send 4 rays randomly towards the light. We know that they should intersect the light unless they intersect some other object. We see that of the 4 rays, 3 of them intersect the light and 1 of them does not. So that means that this point here is not completely visible to the light, and it will not be as brightly lit as, say, a point up here, which is perfectly visible to the light. So we're going to average the contributions from each of these. And the effect that we get by doing this is something that is naturally appearing, and that is soft shadows. Shadows do not have these harsh, perfect lines. It's not to say that you can't create something very similar or almost perfect to this, but in general, shadows are soft. They have soft edges. And by doing this area light calculation, we also get our soft shadows. So what does that look like? Well, here I have created a rectangular light source. And I have the same sphere as before. And what we're going to do is we're going to ray trace this. So there's no point source anymore. Now I just have this area light, which is a rectangle in front of the sphere. And when I ray trace that, this is the result that we get. Now you'll note that there's no light being emitted towards the back part of the ground plane, and that's because I've set the area light to emit only in one direction. Many applications will let you emit it in both directions, but I only wanted to light the sphere, so why would I send light rays behind myself? You can actually see in the reflection on the ball, now you can actually see the light source, which makes sense because it actually is a physical object in space, even though we can't see it here because I told Houdini not to actually draw. And then the shadow on the ground is soft, and it looks more real. It feels like a more realistic lighting model because it is. Now, how do we get nice results like this? You're going to have to send a lot of rays. If you don't send enough rays, then the soft shadow won't be very soft. It will be very grainy and still kind of harsh. If you actually want a really nice soft shadow, you need to make sure that you're sending many secondary rays. If you don't, it's just not going to look nice. It won't be nice and smooth. And that means, unfortunately, that using area lights is quite expensive because you are sending a lot more rays now for secondary lighting. And there's many, many other kinds of lights. There's something called a spotlight, which is really implemented by many applications as just a point light that has a particular cone under which it emits light. So we have a point light, that's the position of the light, and then it's only going to emit light in a cone towards a particular direction. And so when you send the ray, the secondary ray from the surface intersection point towards the point light source, if that ray doesn't actually travel through this cone to hit the point light source, it's not going to be lit by this light. And you'll see here it says that you will get a harsh shadow because this is still a point light. So if you look here, we have our sphere again, but we still have a harsh shadow. Now the one thing you will note is that the way that the spotlight is lighting the ground plane is soft, and that is because of the Lambert's cosine law. You would actually get that with a point light as well. That's to do with the amount of intensity seen on a surface is related to the angle between the normal of the surface and the incident light and the viewing angle. So this does actually play a role, and you get the soft lighting, but you still get a harsh shadow. And there are many, many other types of lights. So if you actually open up Houdini here, let's actually just do that. Let's grab it up. I've got my lights and cameras panel open here. We have a point light. We have a spotlight, which is just a variation of the point light. We have an area light. We have a geometry light. We have a volume light, a distant light, an environment light, a sky light. And then there is a global illumination light, a caustic light, a portal light, and ambient light. Those are all of the different default lights that have been implemented in Houdini. It's a lot. All right, so looking at just a geometric or a volume light, essentially what we're saying here is instead of a flat shape being the emitting surface, what we're saying now is that a particular piece of geometry is now emitting light. So for example, the dragon in this image might be a light source. I wouldn't personally do that, but you could do it. And there are different ways that you could implement interactions with a volumetric light. One way is you could kind of treat it as similar to an area light, but now instead of having light just emitted from a flat surface, light is being emitted from the actual surface of the volume, which means it's being emitted in all directions. And there's even a possibility, because of the shape of the mesh, that it's not emitted equally in all directions, because if you have certain shapes like this and they're all emitting light out from their surface, then a point in the middle is going to be seen by all of those volume points, and therefore will receive more flux from the lights than the others, than other shapes. Now, sometimes we make these shapes visible, but sometimes we don't. So it really depends on what you want to do. In the case of things like maybe light bulbs or lava lamps or lava, which are all volumetric light sources in reality, we might actually want that light source to be visible. It's really up to you on how you want that to be seen. And again, one of the ways to implement this is very, very similar to an area light. You're going to generate a bunch of random points that are on the surface of the light, and then you are going to send rays from the surface intersection point that we had to each of those randomly selected points on the volumetric light, and then we can average the contribution from each of those rays. That's one approach that you could take. There are others. And this is what you get when you use a volumetric light. Now, I have elected not to render the light itself, but if you look in the reflection on the sphere here, you can clearly see that the light source I used was a torus. Because everyone wants donut-shaped lights, right? That could be fun. So I've got this lovely little donut-shaped torus. And one of the things you might note is that we have soft shadows, and the light is being cast softly onto this ground plane, but it's really grainy. And the reason why it's really grainy is because we didn't use enough rays. We'll talk about that later today. Now, there are many, many other types of lights, as you saw, environment lights and skyboxes. That is where you actually have like a distant light that is a volume, like it's a sphere or a box, and it could be a solid color or it could be an image, and the intensity of the pixel in the image is the intensity of the light at that point in the light. And the idea of an environment light like this is you can take an image of your room and use that as a light source to your artificially rendered scene, which means that now the reflections on the objects are going to be reflecting things that actually are in your room, even though those objects that you're rendering aren't physically in your room. So environment lighting is really cool like that. And skybox is generally the same idea. Sometimes it's just like a computer-generated sky. And there are various ways, again, that you can implement these, but a simple way to do it is, again, from the point of intersection on the object, you're going to send a large number of rays randomly out into the world. towards the environment map or the skybox, and then you average the contribution from those particular rays. It's one way you can do it. You get soft shadows from this as a result, and you are also, because you are sending rays towards this image, you're going to get a reflection of whatever that environment map is, or skybox, on the object itself. So it's pretty cool. And we can show you what that is. So this here, yes, I know it's very, very grainy. We will talk about that. So I've got my red sphere, and I've got a slightly reflective plane down here. And I'm using an environment light, and it's just one of the default ones from Houdini. I think it is of a parking garage. And if you look in the reflection of the sphere, you can actually see some of the elements of the parking garage. There's a concrete pillar here. There appears to be a light and a light and a light. So you can actually, it's as if I rendered this scene in a parking garage, even though I didn't, because this is an artificial mathematical object living in my computer's memory. So it's kind of neat. You can see here we get soft shadows and soft reflections, and that is because, again, we are using several rays to do this. But it's really, really grainy. Again, we'll talk about that graininess later. All right. So we have a lot of different objects. We've talked about all the lights that we're going to talk about for now. And the next thing we should be talking about is the different kinds of materials that we can have in our scene. We've only talked about a few basic materials. We talked about Lambertian or diffuse objects. Those are objects that are reflecting light equally in all directions. We've talked about Phong and Blinn-Phong materials, which are objects that can actually exhibit a shininess property, so they look like shiny plastic. But the world is not that simple. This dress is fairly diffuse, actually. But it's not a solid color. It actually has a texture, a pattern to it. And the surface is a little bit bumpy from the weave of the cloth. And so it doesn't necessarily reflect light equally in all directions, but it also has many different colors on it. And our models of materials we've used so far can't do this, so we need to consider that. There are lots of other different kinds of interesting materials out there that we need to be able to model. There are objects that actually have like a physical texture to them, like bumps on their surface. For example, this mouse here, if you look very closely, you can actually see it's faceted in some of the different areas. Now you might be thinking to yourself, but shouldn't that just be captured by the mesh? Yeah, but not always. And we'll talk about that in a few minutes. Then we have objects that are actually reflective. So we've talked about things that are shiny, but we never actually talked about objects that are actually physically reflecting light, like a mirror. And that's an important kind of surface that we see in our everyday world that we need to be able to model. We also have objects that are transparent. And so we, like a glass. I have a bottle of pins here. So this little glass, it's plastic. This is a transparent object, and light is going to need to interact with this. How does the light interact with it? How do we draw something like this with a computer? Then we have surfaces that are anisotropic, and that's where the visual properties are depending on the viewing angle. So over here it may look one way, and over here it may look a completely different way. And then we have, sorry, this is another semi-transparent object. It's a little plastic clip used for sewing. Then there's objects that exhibit subsurface scattering, where underneath the surface of the model, instead of light reflecting off the surface, some of the light actually enters and then reflects off of the internal structures. And something that exhibits subsurface scattering is actually your skin. And before we actually modeled or did any subsurface scattering, skin rendering was really, really bad and looked really plasticky and uncanny. And now that we have subsurface scattering and a lot better models of the light interactions that we can have, we get a lot more realistic skin out of rendering engines. So we're going to start this topic of different kinds of materials with textures and texture mapping. And I always find it really funny that we call it textures, to be honest, because I see it more as patterns. And at the same time, it's not patterns, because if you hear the word pattern, you're thinking it's repeating. But when I hear the word texture, I think of something that I can feel, not something that I can see. But in computer graphics, this is actually called textures. And the act of texture mapping is actually taking an image of a pattern or a photo and mapping that to the actual mesh, and such that when you intersect the object at a particular point, we are going to look up that point's color from the texture map. So that way we can get something like the pattern on this dress. So that's going to let us do wallpapers. Maybe you've got a framed photo in your rendered scene. Maybe you've got patterns on clothes. Maybe you've got patterns are everywhere. Pictures are everywhere. And that's how we get this. So texture mapping is one of the things you have to keep in mind here is if you're going to use it, and we do use it quite heavily in rendering, is that it's very important to use a very high quality texture, something that actually looks realistic and is provided to you at a very high resolution. Because as it is wrapped around the object, it may get stretched or distorted or shrunk or blown up, and if it's not a good quality texture, it's not going to look very good. Now, what's really interesting is historically, and even to this day, texture mapping is used to hide the fact that we may not have as many polygons in our mesh as you think. And maybe some of you haven't played some old games from like the N64 era, so the mid-90s, or just 90s, early 2000s games. There was a serious restriction on how many triangles you could have on the screen at any moment. And yet we still have beautiful games like Ocarina of Time. And we were able to achieve this through textures and the next topic, which is bump mapping. And you can pave over because you put this really super detailed, beautiful texture on a very simple mesh, and it makes the mesh look a little bit more detailed than it actually is. And someone, Ocarina of Time did it, the Final Fantasy series has done this, every video game manufacturer does this. You've got, a brick wall. You could model those bricks. You could model the patterns of each individual brick and paint them red and give them some different properties. But that's really time consuming for artists to actually create that. And it's not just that, it's costly in terms of actually, rendering something like that, because you would have to have a really precise mesh and then paint it a perfect color. Whereas I could just have a wall, flat wall, and put a really pretty texture on it. It's probably good enough. Well, depending on your game. So textures are actually one way that we can provide realism without increasing the complexity of the scene too much. So here's an example from Houdini. I've taken a couple of textures which are publicly available and just mapped them onto a ball and the floor plane. It's not very pretty. There are many different ways that you can actually map textures onto the object. And it's really up to you which technique that you use, you and of course your rendering tool. Now, when I implemented my own ray tracer, I used very simple texture mapping techniques that don't necessarily give the best results, but they technically work. So I actually used what's known as a cylindrical projection. And that is, you can imagine that around, this is the only, aside from a can of pop, this is the only cylindrical object I have. You can imagine that this cylinder here is where the texture actually is living. And it's really easy to do that. We have an image and we can just, you know, roll it. We could do that with our hands. And then we're going to put the object we wish to apply the texture to in the middle of the cylinder. And then when I want to know what color this particular pixel should be, I send a ray from the surface intersection point along the direction of the normal to intersect the cylinder, which is the rolled up image, and that gives me the color. Cylindrical projection. Very easy to implement. Doesn't look so good in practice. Always. The reason why is because what about the roundness of the top? You end up with the things at the top being all stretched and weird like. There's also spherical projections where you're putting your object in a sphere and the texture is on the sphere. There's planar projections, box projections, and these are all very simple to implement. And it's not that they can't look good. They can look good. But if you were to just take a regular photo for something like a spherical projection and say, okay, project it onto a sphere, and then use that spherical projection to project it onto the object, it's going to get all stretched out. Now, the trick here is to actually manipulate the texture image you're using for the spherical projection in advance, such that you're warping it along at using like polar coordinates in advance. So actually properly like stretching the image. And then when it gets put onto the sphere, it will look right. And so that can work for certain things. Doesn't always. Another way we do it is vertex mapping, where we are actually going to map each and every vertex of the mesh to coordinates in the specific image. So this triangle here maps to this triangle in the actual image texture plane. And that is what you see more commonly done in things like video games and films. So we've already kind of talked about this. So planar, cylindrical, and spherical mappings. Again, you've got some intersection point P on the physical object, and you're trying to figure out which point on the texture that actually maps to. And we use this idea of projective geometry. It's not too hard. Once we have the point on the projective geometry, so a cylinder, the plane, the sphere, those coordinates on the cylinder or the sphere map to a 2D coordinate in the actual image. And we refer to those coordinates in the actual image as UVs because it has two components, an X and a Y. But instead of trying to confuse you between X, Y, and Z, the axis in the actual rendering program, we've been calling them UVs. And if we're doing vertex mapping, of course, then each of the vertices in the mesh are actually going to map to a specific UV in the texture map. And if you download models off the internet or you're creating models of your own, you will often create a UV map. Or if you have like an OBJ file, it has UVs in it sometimes. And that's what they are. It's telling you where in the image plane that particular triangle has to live. So just borrowing these images for what the mappings would look like, I borrowed these from the Foundry. So if we have a planar map, so this is the Teapot. And I'm sure if you've been around rendering before, you've seen this Teapot before. And you might be wondering, why does everybody use this Teapot? It's everywhere. Where'd it come from? So the story behind the Teapot is this is actually called the Utah Teapot. And once upon a time, a long, long time ago, when people were starting with computer graphics, there were very few models out there to actually do all these different tests on. And we needed some models that had some different properties, convex and concave surfaces, some sharp edges, and so on. And so my understanding is they had this old Melita teapot in the lab at Utah, and they scanned it, and they used it in their paper in all their papers as one of the test models to show certain lighting equations. And it's kind of become pervasive throughout computer graphics. It's the mascot, is effectively for computer graphics, is this teapot. It's like a 70s Melita teapot. I think it's a 70s one. The actual teapot is a little bit taller, so the scanned one was a little bit squashier, but you can actually go see this teapot. It exists. It's at the Computer History Museum in California. I'm not sure if it's the actual one or just the same model. Yeah. We use this teapot for everything. So you can see here how when we have a planar projection, when it gets projected, that texture gets projected onto the teapot. The top of the teapot, the checkerboard pattern looks unstretched, undistorted, but along the sides of the teapot, we have a really badly distorted checkerboard pattern. So maybe this isn't for us. But for some surfaces, like if I just have a plane, why would I use anything other than a planar projection? There's also a cube projection, which is just taking this idea and you're looking at the surface normal and you're saying, okay, so if this surface normal is here, then it's pointing more towards the plane above me, so I'll grab the texture from there, or it's down here, so it's pointing more towards, you know, the side of the box. And you can see here that the checkerboard pattern is less distorted, but there are seams. Could work, especially if you're just projecting onto a box. My personal favorite is the cylindrical projection because it's really easy to implement. And it does a really good job of the sides, but it does a really awful job of the top. The top of the checkerboard pattern you can see here is very badly distorted. Oops. And then we have the spherical projection here, which the sides look very reasonable and the top is less distorted, but you can actually see that we have a problem where the checkerboard pattern itself actually starts to get really, really tiny. So it's generally, it's better in some cases, but again, none of these models are perfect. In fact, they're all kind of off. Very easy to implement. Certainly there are objects where these are a great solution. Not all objects. The problem is with something like a face or a hand or a tiger. I don't know why I thought of tiger. I want to say this pin, but I think, oh, you can't even see the pin. It's a yellow pin. This red pin. This red pin, which I have now dropped on the floor and will surely step on at some point because I'll forget about it. The red pin, better grab another one to drop on the floor. This lovely blue pin. We could probably use a cylindrical mapping for this, but some objects, it's not going to look good. So for example, tigers, animals, horses, there's too much details. We want the eyes to actually be where the eyes should be and the nostrils to be where the nostrils would be. We want the musculature and the fur to be pointing in the correct orientation and not being distorted. And if we use any of the projective geometry techniques, there's going to be some distortions. It's inevitable. It's not going to look good. So the other thing that we could do, as we've mentioned, is this concept of vertex mapping, where we are literally going to take every single triangle or quadrilateral from the mesh and map its vertices to a region of the texture image. And then the idea is for that small triangle or quadrilateral, we are going to pre-distort and insert just that small region of the texture there. And then we will grab it from that and map it exactly to the correct point of the actual image. So that's pretty cool. Now this is something I don't personally do, is make these texture maps. So this is an image from the Lightwave 3D guide, and a lot of these tools actually have the ability to unwrap the UVs. And effectively what they're doing is they're taking the vertices from the mesh and creating kind of this picture here to let you know how these pieces are going to map onto this surface. And then you can go take that and draw manually into this and then come back and it will merge together. So this is what a UV texture map would look like. And these, in my opinion, take a bit of art to create nicely. It's not something I do because I don't do a lot of rendering for this kind of thing, but you can definitely do it. So textures, we've kind of got a handle on that. It's not too bad to do. If you want to do it in something like Houdini, it's fairly straightforward. You're going to go into your material palette. Now they have a bunch of basic ones down below, but I like to use this principled shader. And if you go into principled shader, there is this option here, textures, and then you can click use texture for the base color, and then you can choose a file for that. And what's really interesting about a lot of these different tools is that you can actually, you don't just have to have a texture for the base color. You can have a texture describe the shininess of the object, so the object might be shiny in some places and not others. You can have the texture describe the reflectivity. It's pretty neat what you can do with that. So I kind of think that's neat. And if you're looking for textures for this course, there's many places that I would recommend that you go to. Of course, you're welcome to use any of your own created content, but there's public domain textures, free stock textures, Turbo Squid. I do not require that you pay any money for the course, but if you are going to use freely available things, make sure they're actually freely available. All right, so I have my beautifully patterned piece of clothing, but it's perfectly smooth. So here's the problem. When we're creating a mesh for something, as we've kind of seen from the performance of ray tracing, the more triangles and the more objects that you have, the longer it's actually going to take to render, because the number of ray object intersections is going to be very large. So ideally what we need to do is reduce that, and often what we will do is simply reduce the sophistication of the mesh. Okay, that comes at a cost. So suppose I had that brick wall and I wanted to make it very simple, so I just make it a flat plane, perfectly smooth plane. Oh, I got a book here. I'll use this book for this example, one of my favorite books, Grammar of the Film Language. So I've got this beautifully smooth wall. It's going to be a brick wall. So I apply a texture to the wall, but it's still a perfectly smooth wall. And so the light reflects off of it as if it's a perfectly smooth surface. Now, I don't want to add any more polygons because it's going to be too expensive. So how do I turn this perfectly smooth surface into a bumpy brick wall without changing the mesh and adding more triangles? Well, that, my friends, is where bump mapping comes in handy. What bump mapping does is it changes the normal. So we know from the lighting equation that the normal plays a role in the lighting of a surface. So what happens if the normal was here and I move it a little bit? Now that point on the surface is going to be rendered a little bit differently because the normal is no longer pointing perfectly straight up towards the light. Now it's pointing a little bit away from the light. So it's not going to receive as much light from the source. And so it looks like in our brains that there's a bit of curvature to the surface or roughness, even though it doesn't exist. So what bump mapping is very similar to texture mapping in how we can do things like projective geometry to map the bump onto the object, or you can use UVs to do this. But what bump mapping does is we have an image that is going to be used to perturb the surface normals. So when we have that point of intersection and we are now using the point of intersection to get the surface normal, we are looking up a perturbation factor in the bump map and applying it to the normal of the actual surface to shift its direction and make it look like it's bumpy surface. Hence why it's called bump mapping. And if you combine bump mapping with texture mapping, you can take a perfectly smooth, flat surface and make it look like a rough, bumpy brick wall. Except the cost is really cheap because we have just one quadrilateral. It's pretty cool, right? I think it's pretty cool. And this is what a lot of video games are doing to you, to give you the illusion of super high rendered polygon geometry. It's totally not. So the idea is when we are actually perturbing the normals, there's different ways that you could do it, but technically most people, what they do is the intensity of the pixel in the bump map is added to the normal to produce a perturbed normal. Now the problem with adding two vectors together is, of course, now they're not normalized. So we would have to do one additional step after the perturbation, and that is to actually normalize the vector, make it so that its length is equal to 1. So what you can see here is this is a plane surface, and now we can apply some bump mapping. We have a cube, a sphere, and a ground plane, and they're all perfectly smooth, boring. And our bump map, you'll often see them rendered like this, kind of in purples and magentas. These values here are telling us how much to perturb the normals by. We apply this to these objects, and look at that. They look bumpy. This doesn't look like a smooth surface anymore because the light is reflecting differently off each part of them. I see the wood grain texture here. It's great. But I didn't technically change the models. It's cheating. But it looks great. Now, look very closely. You can actually see this in games with low poly counts, especially something like Ocarina of Time, where they are using bump mapping and texture mapping. All you have to do is look at the edge, walk up to any edge, and look at it so it's like you can see it. You will see a perfectly straight, smooth line, but it looks like that's perfectly perfect. But the texture on the faces that are around that edge looks like it should be bumpy. So you can tell when games do this because of that. You look at the edges. It's one of the ways also to win at the Faker Photo Challenge is look at the surface edges, because if the surface looks bumpy but the edge is perfect, they're bump map, and therefore it's not real. So it's a good way to do it. Again, this is technology that we use whenever we have lower resolution meshes to make things look more realistic. And the hope is that people aren't going to be sitting there, what is this I'm looking at? They're going to be like, I better shoot this guy because there's enemies coming at me. They're not going to notice because we don't generally notice unless we sit there and inspect every detail. And I'm not going to lie, I do sit there and do that. It's my job. Now, the other thing I want to say is that there are other approaches that we can do. We can actually take a map like this, and instead of perturbing the normals, I can actually subdivide the surface and perturb the vertices themselves. And that's a technology that we do use now, but it's obviously more expensive because we're actually manipulating the geometry itself. Whereas bump mapping doesn't manipulate the geometry at all. Right. So, lots of different kinds of things that we can do. We now have the ability to make something have a pattern on it, and we have the ability to make it not look perfectly smooth like plastic, which means the amount of realism we are getting out of our ray tracer now has gone up. We've also got soft shadows and environment lighting, so we're getting to a point now where we might be able to produce some convincing images. Or hold my beer, because no, actually we forgot some things. What about reflections? What about refraction? So looking at reflection, we note that many surfaces are in fact shiny, as Phong and Blinfong's models indicate. And so some objects should actually be reflecting the scene themselves. Don't actually have a mirror, so I can't hold one up. But even things like, you know, the actual pin part of these pins, they're metallic. It's silver colored. It should be reflecting light. Well, color. And so this is mirrors, this is glass, this is enamels, this is metals. They all reflect the scene. And so we need to be able to simulate that actual reflection in our models. Now, we often use the shininess parameter P to indicate how reflective an object is, but that's not necessarily the case. That's a nice spelling mistake. So what we should be saying here is lower values of P, which would create a more diffuse surface, create less reflection, and higher values of P produce more reflection. Apologies there. Some materials also give reflectivity as a separate parameter. So you can have an object that is shiny but not reflective. That's entirely possible if you separate P from the reflective parameter, which I prefer to do because I want to be able to have shiny objects that aren't reflective, even though that doesn't really represent our reality necessarily. I mean, it kind of does because, oh, that's a pin you can't see. Let's grab more pins so I can step on them. This object here, the plastic is shiny and white, and it's reflective, but not, I wouldn't say I can see myself in the reflection on this. I can see a reflection of the lights around me, so I'm getting the specular highlights. So this is a good object for Blin-Phong or just Phong reflection model, but I don't need actual reflectance to do this one. So sometimes it does make sense to separate P from that. So if we do this in Houdini, we can actually turn reflections on and off. And so we have that red ball on a reflective surface. And look, we can actually see, I used an environment light here. You can see the environment in the light, and you can see the reflection of the ball on the surface. So that's pretty cool, right? So how do we do this? So this is the same thing, just with no reflectivity and no Phong shading. Reflection? No reflection. So now we've got, so just so you can see them. So this is our goal. This is all diffuse surfaces. This is what happens when we have Blin-Phong Blin-Phong lighting model. So we have shininess. And this one here, you can see here that it's not perfectly shiny, but as we increase the amount of shininess and we enable reflection, now we can actually see the reflection of the ground plane in the red sphere. Looks more real. So how exactly are we going to achieve this particular look? So reflection means that we are actually going to need to send some more rays into the scene, because I don't just want to know what is the contribution of the incident light source. There's also the possibility of objects that light's going to reflect off onto this from other objects. So I need to actually send a reflected ray into the scene to see what that ray can see, because whatever that ray sees, I will be able to see on the surface of the reflective object. So we compute the contribution of the light, and then we are going to actually compute the the angle of reflection to figure out what new ray we send to see what reflection we see. So we are not going to be using the light ray for this particular task. So given our surface and our surface point O, we have a normal to the surface. And Q and P are our two rays. So P is our incident light. That is, sorry, not incident light. That's our view ray. So this is the angle on which I am viewing the surface. And it makes a degree, it has an angle with the normal that is theta degrees. Reflection is going to be the same angle coming on the other side of the normal. So Q is the reflected angle, and the angle of reflection should equal the angle of incident. So how do we compute that? Well, there's a lovely little formula for that. So we can compute the reflected ray Q by taking the view ray and subtracting the 2 times the normal of n dot p. So that is the normal of the surface and the view ray. And this is a fairly simple computation to do. And with that, we get ray Q. And what we are going to do with ray Q is we are going to send it out into the world and ask it, what color do you see? We are almost recursively doing the ray tracing now as if the point on the surface of the original object was the camera, and we're asking, what do you see? And so that ray is going to intersect another object, hopefully, and we are going to then compute the color of that other object given this incident ray, this view ray. And then we'll return that color to the originating object and use that color as part of the equation to figure out what is the color of this particular point on the surface. But what if the object I intersected is also reflective? So, for example, what if I have this pop can and I have a mirror? And the ray, my reflection ray from the pop can hits the mirror. Well, in order to compute the contribution that the mirror makes to the pop can, the mirror needs to send its own reflection ray. And so it sends it into the scene and it hits another mirror. So in order to compute the color of that point on the pop can, I need to compute the color of the point on the first mirror. And in order to get the color on the first mirror, I need to compute the color on the second mirror. The problem we get with reflected rays is they could bounce around the scene infinitely. You just keep going back, forth, back, forth, back, forth, back, forth. That's gonna be a big problem, even though this is perfectly natural. From a computation perspective, it doesn't really make a lot of sense, because you could have an infinite number of rays just bouncing back and forth and back and forth and back and forth. Are they really contributing anything? Maybe small amounts? But at some point there's going to be a fall off where those reflected rays don't contribute anything noteworthy. So typically what you're going to see in a ray tracer is a reflection limit. And if we actually open up Houdini here, and I'm going to go into Mantra's properties, under sampling, not sampling, limits, you'll see reflect limit and refract limit. The reflect limit is how many times can you send a bounced reflected ray before we stop doing it. And the reflection limit is set to 10, which is pretty high. I don't really, I mean, there is a difference between like 5 and 10, but it's questionable whether you need it. Depends on the scene, of course. But you can change those things. So what kind of a visual impact does that actually have? So this is when I set the limit to 1. And you can really see the impact of the bounced rays in these examples. I've got a few examples here for you. So when the limit is 1, I can see the reflection of the ball in the mirror that the ball is sitting on. And I can see the reflection of the ball. There's not 3 balls in this, by the way. It's 1 ball and 3 mirrors. I can see the reflection in the ball in the right mirror and in the left mirror. But I cannot see a reflection of the mirror below in the ball. So when I set the limit to 2, look at that. There's now an additional bounce. And so I am seeing not just the ball and its reflection, but the reflection of the ball and its reflection sees the ball and the reflection. You know, this is turning into a tongue twister here. So that's what I get when I set the limit to 2. Now let's set it to 3. You can see here there was a reflection in the center at the back, and it only has the ball when the limit is 2. And when I increase the limit to 3, it gains the reflection. And all of the other ones, I'm not sure if you noticed here, look at the specular highlights, so the reflective highlights. You can see as we increase the limits, the amount of those reflected highlights increases. So 1 bounce, 2 bounce, 3 bounce, 10 bounce. And you might be like, well, I can't see a difference between 3 and 10. But if you look really closely, especially at this center top one, you can see here that there's some specular highlights that start to show up with 10 bounces. So let's look at another scene that's a bit more complex. So this scene has just a point light because I didn't want it to take forever to render. And we've got mirror walls and a shiny floor and a shiny ceiling. I think it's a shiny floor and a shiny ceiling. This is when the limit is 0. That is, no reflection happens whatsoever. I have a shiny red torus, and I know you can barely see it, but there's a shiny blue horse statue. When I set the limit to 1, now I can actually see the shiny blue horse, and there is some reflection of that horse in the mirror behind, and I can actually see the torus, and I can see the reflection of the torus in the mirrors around it. No reflection? Reflection. Things are starting to look a little bit better. So this was Lecture 3's ray tracer, and this is Lecture 4's ray tracer. Now let's increase the limit. This is 2. Now I can actually see the reflections of the objects in the floors, and I can see the reflection of the objects in each other. Look at that. None, 1, 2. It's starting to look more and more realistic. Now I'm going to turn it up to 3. 0, 1, 2, 3 bounces. You can see here now that we are this reflection over here is being reflected from over here to over here. So we have 3 bounces happening. And so we end up with more and more reflective copies, and it's starting to look better lit. It looks shinier, and the reflections are looking more realistic, like the way we would expect them to behave under these circumstances. Now we can crank this up to 5. So let's do this again. No reflections. 1 bounce, 2 bounce, 3 bounce, 5 bounces. It's looking really good, isn't it? And here's 10. So it's hard to see the difference between 5 and 10, but if you look here in some of the details in the horse's mane and the interior part of this torus, you can see here between 5 and 10, it gets a little brighter with 10 as more reflective content is brought up into these surfaces. So as we increase the reflection limit, it's going to have less and less of an impact as the numbers get bigger. So you ramp up in realism, and then finally you kind of plateau off as this is not adding any additional, which is why 10 is actually a decent number. So this is actually very simple to implement, by the way. What you're going to be doing is, if you are implementing reflections, you're also with each of your rays going to pass around like a counter. And so it's like, this is the first bounce. And then when you make the next ray, you say this is the second bounce. And then before you make a new ray, you ask, is this bounce number greater than or equal to the maximum? If so, return the color, otherwise keep bouncing. I wonder, is this going to impact the performance? Obviously it is. Okay. So the next thing to talk about then is refraction. This one is a little bit more complicated. When a light passes through a transparent or translucent object, we can see the thing that's behind. Okay, that's easy. We know that. If you hold up a clear object, you can see through it. My glasses, you can see through them. It would be really weird if you couldn't. And you know, your glasses, windows, you can see through a window. So this is the idea of transmission. Things on the other, you are seeing things on the other side of the object. And you might be thinking, oh, that's not so bad. So what you're telling me is that I intersect an object, and then I just keep going to see what else I intersect. And when I finally intersect an object, keeping going in my original direction, that is not transparent, that is, it's opaque, then I return that color, and that's the color of my object. Not quite, because that's not taking into consideration the material that your transparent object is made out of. What's really interesting about refraction is that light bends. It bends. And I know it's weird to think of light bending, but it does. It bends as it travels through different surfaces. And what's actually going on here is when light travels through different materials, the structure of those materials will actually slow the light down. And different materials will slow the light down different amounts. And what's further interesting, just as a discussion for another time, which we will discuss, some wavelengths of light are slowed down more than others. So what happens when you slow down the speed of light is that it gets bent, or at least it appears to be bent. And we need to be able to simulate this actually happening. And so first thing we need to know is, how much is the light actually going to bend? And that is this thing called the Index of Refraction. It's actually the ratio of the speed of light in a vacuum to the speed of light passing through the material. And the idea behind this is that if the index of refraction is small, then the light really isn't going to bend. For example, the index of refraction for air is roughly 1, which means that as light travels through air, we do not anticipate that it's going to bend. It goes straight from the point source to whatever thing. However, if the index of refraction is larger, for example, diamond is like 2.417, then the material is actually reducing the speed of light by a fair bit, causing a fairly large bend. And so instead of the light going through the diamond straight, it enters like this and then exits like this. And so what we see here is not from what's up here, it's from what's over there. So there's a little bit of work that needs to be done. So here's just a basic example of transparent objects in Houdini. The dragon is using the index of refraction, I think, for just glass. And I believe the red sphere and the torus are both using the index of refraction for diamonds. So it's much, much higher, which means that the light is going to be bending a lot more. And you can kind of see it here because I don't actually see through the ball here, or the torus here. And I'm not really seeing through the ball here to just the floor, which means that the light isn't just going straight through the sphere, oh, sphere, boop, and getting the color of what's behind it. It's actually bending it, and so it's getting the color from elsewhere. And you can see that up here as well through the tail and the neck of the dragon. We're actually seeing the floor, and we're seeing the floor due to just the refraction of light and the reflection as well. Now, excuse me, I wanted to demonstrate for you what it would look like to render with different indexes of refraction. So I have the index for air, and I made a cylinder blue air. And then I put this red cylinder in the middle of the glass so that you could see what happens. So when we have the air, you can see here, it doesn't look like a light is being bent at all, because it's not really. And then I set the index of refraction to be that of water. And you'll see here, we go from no bending to bending. And you don't just observe it in the straw, we're also observing it here in how we see the ground plane's intersection with the rear wall. With air, there's no distortion. With water, there is a distortion, and that's because we've altered the index of refraction, and now light is being bent. And so as a result, the refracted rays are not going in the same direction as the view ray is. They're going somewhere else. Now we can increase that index of refraction further. So this is glass, and then finally diamond. So just to show you that sequence, this is air, water, glass, diamond. And with each one, you can see that the amount of bend is increasing. Oh, this one's sapphire, it's not even diamond. There's diamond. Sapphire is kind of halfway between. So there you have it. That is the impact of the index of refraction on our surface. So here's a handy little table. You can grab this table from Wikipedia or 100 different resources on the internet to let you know what the index of refraction is for many common materials. So things like air, water, oil, glass, sapphire, diamond, all of those lovely things. Sorry, it's like 2 in the morning. Now, you might be thinking, 2.417, that is the biggest index of refraction I can use. Actually, there is a gemstone material that has an index of refraction that's higher than diamond, and that's called Moissanite, which is really interesting because it's it can actually looks very much like a diamond, but it's some people actually consider it, quote, prettier because it has even more fire than a diamond because its index of refraction is bigger. And just to give you an idea of what do you mean, when we think of diamonds, and I'm not a jewelry person, but many people are, people think of that characteristic sparkle. They're just so sparkly. And that comes from 2 things. Number 1, it comes from the cut of the stone, having many different faceted surfaces in which to reflect light. The other thing that we're getting from a diamond is the fact that it has a high index of refraction, and that's going to play a role in something called total internal reflection. So this is the same model rendered with glass on the top and rendered with the diamond index of refraction on the bottom. And what you should see here is the glass one is interesting, but it's not very sparkly, but the diamond one is much more interesting and much more sparkly. And yes, you're like, but it's so grainy. We'll deal with the graininess still. Don't worry. So this is kind of a diagram to show you what's happening. So you get the bending of light when you have the interface between 2 different materials, and air is a material, by the way, and you have two different indexes of refraction. So if the two materials have the same index of refraction as we saw, you get no change. But as the index of refraction increases, we would actually start to get bends. Now, you don't get any bend if it goes straight, by the way. That's going to stay the same. You get the bend when it's at an angle. Now, here's an interesting property. If the index of refraction for the first object, N1, is greater than that of the second object, we could say incident and excident object, there is a potential for something called total internal reflection. And what that is going to be the light, it travels through the material, and instead of being bent and exiting the material, it actually reflects inside the material. So that is, you're going out of the material, you bounce off the exterior wall and go back through the material again. And that is actually what is one of the things that's contributing to that brilliant sparkle of a cut stone. It's the combination of the index of refraction and the faceting of the stone. Now, computing the refracted ray is a bit more work than the reflected ray. Reflection is easy. Refraction is much, 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 much harder. So the first thing we need to know are the indices of refraction for the incident material and the excident material. And we also need to know, the incident light ray and the transmitted ray, which is what we're trying to find. So the incident ray is going to be our view ray, so the ray that goes from the viewer's eye through the pixel in the image. And what we're going to do is we compute this Z term using a ratio of the indices of refraction, and then we end up with this lovely equation here. I'm not going to go through what this means exactly. I'm just going to say, look, we use this equation and it gives us the refracted ray. We also note that if the squared length of vector z is greater than 1, then this is undefined. And the reason for that is if you look under the square root here, we have 1 minus the length of z squared. That's what these vertical lines mean. We're taking the length of this vector. And the problem is if the length of this vector is greater than 1, then we end up with a negative number underneath the square root, which means we would have an imaginary result, and we don't want that. So this would be undefined, which also means that instead of the light being refracted, it's actually being reflected internally. So that's pretty cool, because you can compute that point where the ray would leave the material, and then you could just perform the reflection from there. That's pretty cool, right? I think that's pretty cool. But that's an interesting thing, because we usually, when we're dealing with surfaces, we only worry about where we hit the material first. And when we're dealing with refraction, we also kind of need to know where we leave the material, because that's the point where the light gets refracted from, or reflected from. It's not where you enter, it's where you leave. All right. Things get a little bit more complicated yet still. Because there are many surfaces in where 100% of the light is not refracted or reflected. Sometimes a material will both reflect and refract light. And in fact, that's what most materials do that are transparent. A portion of the incoming light is going to be reflected, and the rest of the light is going to be refracted. Actually, there's a third component. A portion of the light may be absorbed, but we're not going to deal with absorption right now. So we are getting some light refracted and some light reflected. How do we know how to combine that? So what we can do is there's this thing called Fresnel's equations, and this is them right here, and you can use them in a ray tracer to compute the ratio of the reflected to the refracted light. And then what you would do is you would send not just a reflected ray, but also a refracted ray, get their colors, and then use the Fresnel's ratio that you computed to figure out the contribution made by the reflected ray and the contribution made by the refracted ray. And you can combine them together. Yes, that means that an intersection point on an object may actually send not just a shadow ray, but a reflected ray and a refracted ray. We have lots of rays bouncing around in the scene. But you know, that's reality. And then we can get cool images like this. Now, this is an interesting one. So what I did is, this is a surface that has 100% of the light being refracted because I disabled reflection. So 100% of our light is going to be refracted. That's unusual. We don't typically have human-made surfaces, objects that are refractive but not reflective. But you can do it. I mean, there are cases where that happens, but if you're thinking of like a physical object, that's weird. But it's rendering, so we can do all kinds of fun things. So this is no reflection, and this is when we have refraction and refraction going on. You can see here. It's pretty neat. All right, we're not done yet. So I said light could be reflected and it can be refracted, can also be absorbed. So for example, if I have an orange object, it's a piece of Play-Doh. I have kids, hence I have Play-Doh everywhere in my house. And the orange object is reflecting orange light back to us. But all of the other colors of light are being absorbed, actually, or transmitted. So the other thing to keep in mind is, even if an object doesn't have a clear object, you're like, it has no color. How could it possibly absorb any light? But it can. A very thin thing like this piece of plastic lets almost 100% of the light through. But this plastic isn't actually perfectly clear, and as a result, a portion of the light isn't being absorbed in addition to it being reflected and refracted. And we use Beer's law, or Beer-Lambert law, to indicate how much of that light is absorbed by the object and how much is going to be reflected or refracted. And typically, what we do in ray tracing is we're multiplying the color found by the refracted ray by the absorption coefficient. So we will give the material an absorption coefficient, and then we're going to multiply the refracted or reflected ray by that, so that we are taking into account a certain portion of the light didn't make it. Now, here's the thing. You may not see this in Maya unless you're making a pretty sophisticated material, and you may not see this in Houdini unless you're making a pretty fancy material. And the reason for that is that absorption is typically done on a per component basis. So that is, a material may absorb more red than blue. So it depends on what kind of rendering you're doing as to whether you will see and be able to use this particular law. All right, so is that everything? We can render everything in the world now, right? Well, why don't we talk about diamonds a bit more? So I have this diamond model here. I think I got it off TurboSquid. Don't remember. It's a free one. And it's not the world's best cut, but you know, it's got some facets on it. And I've set the correct color, and I've set the correct index of refraction, and I put some fancy lights in the scene, and then I ray traced it. It's really boring. Doesn't look like a diamond. Now, I'm not gonna lie. Diamonds don't photograph well. And if a diamond looks pretty in a photo, it's probably due to a lot of tricks. They don't photograph well, because you don't get to capture that rich sparkle that a cut gemstone would give you. So this is actually, on the right-hand side here, this is actually a photo of a diamond. And what we're missing here, aside from the fact that this has way more facets than our little stone does, we have not, where'd the color come from? Our diamonds are not reflecting any colors. They're just grayscale and boring. Whereas a real diamond, and if you have one, look at it on a sunny day. Look at it under beautiful lighting conditions. It sparkles with a rainbow of colors, and we're just not getting it. Even with all of this stuff we've gone through so far today, that characteristic rainbow sparkle of a diamond doesn't show up. And in fact, this is not just true for diamonds. If we tried to do any kind of cut stone, any kind of crystal, glass, soap bubble, prisms, none of those objects will exhibit the rainbow effects that we expect. Everything will be bland and grayscale. The truth is, ray tracing that we have shown you so far actually can't do this. It's not to say that we can't do it. It's just that the models we have shown you so far are not capable of doing it. We can fake it. And I mean, this is photorealistic rendering, not physically based rendering. So I don't care how you made it look photoreal. I just care that it looks real. Now this admittedly is a different cut. I was trying to find more realistic cuts that would match this one here. So here you go. Using the ray tracer and only the tools that I've shown you today, and yes, last week, I created this picture here. Now we have a diamond that has the rainbow sparkle. But how did that happen? I thought this wasn't supposed to be possible. Because I faked it. How did I fake it? I made an environment light, and the environment light's pattern was a rainbow. Like, just a repeating rainbow. That's it. And look! It produced that rainbow sparkle. Now, there are some downsides of doing this particular technique. You want to make sure that that rainbow environment light will only actually apply to this little object here. We do not want it to apply to the surface around it, because if it did, then we'd have rainbows everywhere, and that'd be really weird. It's still not perfect, but obviously, because there's a lot of other characteristics of diamonds that we're not simulating here with this, with the ray tracing model so far, but it's definitely better than this one here. So it is possible to recreate some of the visual appearance of diamonds without actually doing any of the extra simulation that we need. How should we actually be making, this is a little bit closer view of it, how should you actually do this? So the issue at hand here, the reason why there's several issues at hand why this doesn't look like a real diamond. Number one, we are using direct lighting only. We need indirect lighting, and our ray tracing model doesn't have it yet. Also, we're ray tracing and assuming that the index of refraction is uniform across all wavelengths of light. That's not reality. The reality is that it's actually going to, the index of refraction is going to impact different wavelengths differently. And that's why you get a prism actually split the colors into a rainbow. White light is actually made of all the colors. And so when you shine a white light at a prism, it should split the colors out. And the same thing is the reason why you're seeing the rainbows in the diamond is for the same reason, is because the light is being dispersed inside the stone and reflected back to you. And in order to actually realistically do that, we need something called spectral ray tracing, where instead of actually just sending a ray, one ray, we are going to send many, many rays for each wavelength of light and perform the lighting calculations, not in terms of an RGB triplet, but actually in terms of the wavelength of light, which means that we need to know not the color of the object, but we actually need to know the spectra of the object. It's a lot more work. We'll talk about it another day. But there you go. It's not bad. It's not great, but it's not bad. And it was cheap. It was really cheap to do this picture. All right. Still so many effects that we are not doing. And another one is subsurface scattering. And I've borrowed some pictures, I think these were all from Wikipedia, of some various different materials that actually exhibit subsurface scattering. So your skin is actually one of the key things that does it. If you hold your hand up to a bright light, even my LED lights here, I can actually see the redness, the subsurface scattering from my skin. Our skin, you know, has a color, but when we hold it up, it usually shows up like orange or red. And that's due to the subsurface scattering. And then other things like opals here in the middle, they have subsurface scattering. They're not opaque, but they're not transparent. They're translucent. So some of they have a color, but they're also reflecting light, not from total internal reflection, but just because they're not completely transparent. Leaves, another great example of something that exhibits subsurface scattering. And what we would do to model something like this is, you know, oh, we might have a model inside where a portion of the light enters the object and then reflects off of the inside surface. So if we were to draw this subsurface scattering, you've got rays of light that are actually reflected, and then subsurface scattered rays means the light goes in, bounces around a whole bunch, and then gets reflected in a seemingly random direction. But that's what's happening to give our skin the appearance that it does have. And opals and all of these other different materials is subsurface scattering. And this is really difficult to simulate. You could actually simulate it. You could actually distribute some particles or another mesh under the surface of the initial mesh and then actually simulate the scattering by actually firing rays inside the object, or between the outer object shell and the inner object shell, or between particles that you've rendered placed inside of the mesh. So you could do that, and that would certainly be a much more physically accurate model for things, but it would also be a very expensive thing to do. And so there are lots and lots of approximation methods that we can use in order to simulate subsurface scattering. For example, we could assume that light bounces only once. So it enters and then bounces in some random direction. We could do that. That would work. We can also make the assumption that whatever we are bouncing around off internally exhibits diffuse reflectance, which means there's an equal probability of the ray reflecting in any direction. So it could go anywhere. It's not a shiny interior surface, it's a diffuse one. That's a fair assumption to make, I think. Many, many approaches. There's a Monte Carlo approach where, and Monte Carlo is a randomized algorithm. We'll talk more about it in the next lecture, actually, where you can randomly generate particles. Again, it's a bit faster, and it does an actual simulation. Lots of different things you can do. You can also do textures, where the actual texture map has kind of pre-baked in the color that you would see from that relative translucency. Lots of ways you can do this. And of course, there's lots of different parameters to control it. So if we actually go into Houdini here, And I mean, again, I'm just doing this from the principled shader. So we can go over to surface. You can actually build much more sophisticated, and I'll show you one, subsurface scattering models. So let's do, we'll go down, subsurface scattering. So you can say how much you want, and then you can say the distance. And you can also say like the depth, like some of them will let you choose the depth. So at how far into the model is it going to, the ray is going to travel before it gets reflected off? Because if you're doing it right near the surface, then it's going to reflect in a very limited number of directions. But if you go a lot and exit very close to where it entered, but if you go a lot further into the object, it's going to be reflected much further from the incident point, the intersection point. So this is a very simple one that you can do, subsurface scattering. Now, there is also in the default, let's do, where is it? Looking for skin. It's funny because every time I look for it, I can never find it. There it is. So skin. So this one here actually has a lot of different layers, and each of the layers has a different color and their scattering distances and so on placed in there. So that's kind of, you can actually build up a rather sophisticated subsurface shader inside of Houdini and many other tools to give that subsurface look. I'm not going to render one for you right now. So what does this actually look like then? So here we have this green dragon, and there is no scattering at all. So we can't see through this, and we can't partially see through this. The light, by the way, is a point light, and it's located behind the dragon. When I set the scattering on and I set the depth to 0.1, this is what we get. This dragon now, you can almost, it's like it's not completely transparent. It's got a bit of translucency to it. We can kind of see through it. It's almost glowing now. It looks like it's made out of jade. And we can alter the parameters so we can reduce the amount of scattering so it's less translucent, and even less so now. And then we can also do things like altering the depth. So this is setting the depth very close to the surface. And you can see here that we're not getting a lot of that translucency. It looks very similar to this one. And then as we increase the depth, you can see here that if you increase the depth too far, we kind of lose that effect. And the reason for that is it's kind of twofold. Number one, because the further into the model that you're going, the chances of the accident light being really far away from you are high. And number two, the fall off for the light and the probability of absorption increase as well, which means less light would actually leave the object. Now, what's really interesting, and you notice with the skin thing, is that we can actually set the color of the light that's being scattered. And that's how we were able to achieve certain looks like skin. So if I actually set the reflectant light to be green, like a bright green, we get a different look too. You can see here, it's nice and bright green. Now you might be like, oh, isn't this just like setting how transparent an object is? Like I could actually say this object is only 50% transparent, which means I take 50% of the surface color of the object and add it to 50% of the refracted component. Isn't this going to give me the same result? Well, let's find out. So here we have the dragon model again, no transparency. Boring. Actually, it looks pretty nice. Now let's set the transparency to 25%. So we are seeing a little bit through the dragon, and again, the light's behind it, but not too much. And then we're increasing the amount of transparency. But we can still really see these well-defined surface features. Even as we increase the amount of transparency, the surface features, like these scales, are still very, very apparent. You can see them. They're there, and they're strong. The difference here with subsurface scattering is that where the light is being scattered, you lose the appearance of the surface of the object. It's almost like the object is glowing, and therefore the surface details in that glowing area become obscured. So, transparency, subsurface scattering. Subsurface gives a bit of glow to it. I just scrolled on the wrong thing. So now let's take a look at other materials. So right now we've made a few assumptions about our materials. We have made the assumption that, things are Lambertian, reflecting light equally in all angles, or they're Blin-Phong, which means they're reflecting light kind of in a rough cone of directions, or they are perfectly reflective, in which case 100% of the light gets reflected perfectly. The truth is that every surface reflects light differently. Some surfaces may reflect light in a particular direction more often than they reflect light in a different direction. And we describe the reflectance of a material using what's known as a BRDF, or a bidirectional reflectance distribution function. And essentially what it's saying is, for each of these directions, here is the probability that the light gets reflected in this direction. So example, for the BRDF for perfect reflectance, 100% of the light is reflected here, and 0% of the light would be reflected in any other direction. So it's 0%, 100%. In this kind of shiny surface, the chances of it being reflected here are 0, but the chances of it being reflected in this area could be indicated by the length of the ray. And then for a diffuse material, perfectly diffuse, a Lambertian material, the chances of it being reflected in any of the directions would be equal. So a BRDF is a surface-dependent function that describes the probability in which light travels in different things. In Lambertian reflectance, the incident light times the color times the normal times the light ray, that is actually the BRDF model function for Lambertian. So that's actually what that term is giving you, is the BRDF. And you can replace this with the BRDF of whatever surface it is you are actually using. So that's kind of cool. Now, we don't always use BRDFs. When we're doing photorealistic rendering, we don't care about things being physically accurate. We just care that from a visual perspective, it looks real. Certainly, physically accurate is probably going to imply realistic. But you tend to see BRDFs used more explicitly for physically accurate rendering. So we might actually say, okay, here is this little clip. Let's actually go and measure the BRDF using a goniophotographer or a spectrometer, and then use that as an input to the rendering model, so that when I am trying to compute the direction that light is reflected in and the intensity of light that gets reflected in that direction, I actually have a function to describe it. I've actually implemented a goniophotographer once. That was fun. All right, so this is the last topic-ish for today, and that is the quality of ray tracing. Now, it kept saying sorry about the grainy images here. Sorry about the grainy images here. We'll talk about that later. Okay, we're talking about this now. You might have noticed that these images were quite grainy, especially ones that used refraction, reflection, and scattering. And the reason for that is because we were not sending very many rays per pixel. The number of samples that we are using to compute the color for a pixel was 1. So you get a very pixelated, noisy image. Let me show you. 1 ray per pixel. It's very grainy. The edges of the objects are very noisy and pixelated. And this is just because we are doing things in a very discrete sense. We are sending a ray. That is the color of that pixel. There's no smoothness, no softness, no anti-aliasing going on. How do we fix this problem? Easy. You send more rays per pixel. So instead of 1 ray per pixel, let's send 4 rays per pixel. 1, 4. 1 ray, 4 rays. Now what happens if I just keep sending the same ray? I'm just going to get the same result over and over and over again. So it's not going to smooth it. So what we're actually doing now is we consider the pixel to not just be a point, but a box. And we are going to send a ray from the eye through a random position in that box. So each ray going through a pixel is actually slightly different. And so we're going to send a bunch of rays through the pixel, slightly randomized positions, and then we're going to get all of their colors and average them. And the more rays you send, the more accurate the result, and the smoother the image. 1 ray, 4 rays. 9 rays. So there's 4, 9. Now you may not be able to see the difference between these, but let me point out the difference. Look at the surface, this gold, shiny, reflective base. It's looking fairly smooth here, but when I go back to 4 rays per pixel, it's actually quite noisy. When I turn it into 25 rays per pixel, it gets even smoother. 1 ray, 4 rays, 9 rays, 25 rays. The more rays we send, the more sampling we're doing, the better color and the smoother this will actually be. I didn't do more than 25 rays per pixel for these, but in the next lecture I send, I think, 64 rays per pixel. Now it's still not enough. Actually, I even think there's a point where I send 225. At this point, the lecture 5 slides are taking a long time to render. Some of the images are taking 29 to 35 hours each. It's a slow process because I have to send so many rays per pixel. And that's the last bit to discuss, is the impact on performance. All of the things we've discussed today actually have a pretty big impact on performance. Stuff like the texture mapping and the bump mapping, not so much. Because we're not really sending any additional rays, but reflection, refraction, the number of bounces, impact on performance. To get the better quality results, we're increasing the number of rays per pixel, impacts performance. To give you an idea, so from before, we said the worst case cost was 2 times the width, times the height, times the number of lights, times the number of triangles in the scene. That was roughly how many intersection tests you were performing. If we now have some reflection rays with depth R, transmitted rays with depth T, now you can add those in. It's not add, it's actually multiply. And then if we then send C rays per pixel instead of 1, we end up with 2 times WHNLRTC. Give you an idea the impact that has. So if we go back to slide 52 here, and I'm just going to type that in here. This image here, just let's take a look at it. Honestly, it's pretty grainy actually. Well, I guess I could just type my number in here. That image took 17 hours to render. 17 hours. And it's not like I have a bad computer. It's being rendered on a Ryzen 9 5950X CPU, which has about 32 cores in it. And Houdini is using all but one. This is getting really expensive. And that's one of the unfortunate impacts of using ray tracing. You get beautiful results, beautiful photoreal results at a steep cost. It's very, very expensive. All right. So we have some review questions here. I recommend that you take a look at them, think about them. If you want to ask questions on Zoom, if you want to ask questions on Discord, by all means, we can discuss these questions here. In the next lecture, we are going to talk about something called global illumination, which we've actually been doing some of already. That's direct lighting. But what we're going to focus on in the next lecture is the indirect lighting part of global illumination and something known as spectral rendering. So that is our next lecture. And then the lecture after that, we're going to look at an alternative approach to rendering using shaders. And we'll talk about how you implement them, the different kinds of shaders that exist, and how they relate to ray tracing and the performance differences between them. So we will see you next week. I hope you have a wonderful week.